2.1 is all about rate of change and limits. We're going to kind of start out, it's not going to feel real connected at first, but I want you to think about how would you calculate your average speed. So if you were to drive from here to Cedar Rapids, you'd see your instantaneous speed, how fast you're going at all times. If you look down at the speedometer, how would you calculate your average speed? You do that by taking the distance you traveled divided by the length of time that you drove there. So I'm going to say change in distance divided by change in time. Now think about, this is really our average speed ends up being our slope, change in distance, change in time. All right, so example 1 says a rock breaks loose from the top of a tall cliff. What is the average speed in the first 2 seconds? First of all, this is going to be our distance formula. In the first 2 seconds, we're going to calculate from 0 seconds to 2 seconds. This is our time interval. All right, so does it make sense? At time 0, I didn't travel anywhere. After 2 seconds, how far did I travel? I just plugged 2 in. 2 squared is 4 times 16 is 64. So my y value is calculating distance. That's going to be my change in y. And my x value is 2 seconds. All right, so my change in distance over my change in time is what gives me my average speed. (64 minus 0 over 2 minus 0). And that's 64 over 2, or 32 feet per second. Now, I was not traveling 32 feet per second the entire time. You accelerate until this gives me my average. So my instantaneous speed is more of an exact moment in time.
Zoe, hi, your ride is here. Zoe, hi, your ride is here. Thank you.
I wish I could turn that off. So say that I want to figure out the instant speed at exactly 2 seconds. How fast are we traveling at exactly 2 seconds? So the way we do that is we say, let's calculate the time from 2 to some time later, say h seconds past 2. So I'm going to call that 2 plus h. In between 2 and 2 plus h, and then I'm going to be sneaky. All right, so first of all, we know that at time 2, we calculated our distance to be 64. I'm still going to use the formula, what did I have that labeled? F of t equals 16t squared. We're still using that formula. Now I'm going to calculate what is my distance at 2 plus h. This seems very ambiguous. Just give me some time and this hopefully will make more sense. So I'm going to find f of 2 plus h. So I need to plug in 2 plus h into my formula, my distance formula. All right, be very careful calculating this. This is 16 times 2 plus h squared, which is 16 times 2 plus h times 2 plus h. Be careful. So this I'm going to distribute. 4 plus 2h plus 2h plus h squared. So whenever you square a quantity, you really square the first, which is 4. You square the last, which is h squared. And you multiply these two and double to get the middle. So 2h doubled is 4h. So whenever you square a quantity, that's what you do every time. Now I'm going to distribute the 16. So this whole thing is my y portion for this. All right. So now I'm going to calculate my average speed. So I do my change in D. So I'm going to take 64 plus 64 h plus 16 h squared and minus 64 y minus y over 2 plus h, my change in time, minus 2. So keep in mind I'm doing my change in distance over my change in time still. My change in distance is my y value minus my y value, and my change in time is my x value minus my x value. So the 64s cancel, the 2's cancel. I get 64h plus 16h squared over h. Do you notice in the top there is a GCF of h, so we can factor out an h and then cancel the h. Now, let's come back to this interval here. If I want my time to be in between 2 and sometime after 2, what value would h have to be to make this between 2 and 2 exactly? Do you see how if h were 0, t is exactly 2. It's equal to 2 on each side. So as soon as I cancel this h here, if I plug 0 in for h here, I get my instantaneous speed to be 64 feet per second. So think about, we started at 0, we accelerated up to at 2 seconds, we're now going 64 feet per second, where the average speed between 0 and 2 seconds is 32 feet per second. So it's kind of like if you drive from here to Cedar Rapids, you might doing an average speed of, say, I don't know, 65 or 70, because that's like stopping at stoplights and things like that, slowing down, speeding up. But the exact moment you pass the Hiawatha exit, you might be doing 70, you might be doing 65, you might be doing 75. Your instantaneous speed is different than your average speed. That's what we're trying to get to, and we will talk about that a whole bunch more. If you feel slightly lost, don't freak out. I think one of the first times I freaked out in calculus was this definition of a limit, because all of a sudden there's all this Greek stuff and it looks super confusing. Let C and L be real numbers. The function f has a limit L as x approaches C. If given any positive epsilon, there exists a positive number delta such that for every x, this statement is true. All right, I don't care if you write this down. I'm just going to tell you this is a good introduction to college when you feel dumb. But you'll get to a point where you actually know some of these symbols. This definition is not critical, but I want you just to understand we're going to learn a whole bunch of notation this year. Okay. Example 3. Notice it says graph this on the calculator. It kind of looks like this, sort of. So it kind of gets closer and closer to the x-axis the further away it gets. There's actually an open circle here at 0. And that's because when x is 0, that puts 0 over 0, which is undefined. So there has to be a hole in the graph. It is defined for every other part of the graph. There's just a hole at 0. My question is, what y value is the graph close to? What y value is the graph close to? So if you kind of trace it with your calculator, you can see it's getting closer and closer and closer to 1. So f of the 0 doesn't equal 1, but what we say as the limit as x gets close to 0 of this equation, sine of x over x, the limit equals 1, because as I get really close on each side, the y value is getting close to 1. So when you find the limit, this ends up being the y value that it's either exactly or close to. That's the big idea for this section. The y value that the graph or the values are close to. So let's investigate that just a little bit. All right, so if we look at all of this, I have 3 different functions. The first function just has a hole in it. Now, you might not remember this, but in the equation itself, there is a hole if a factor cancels from the top to the bottom. X plus 1, x minus 1 is how this factors. If a factor cancels from the top to the bottom, there is a hole at that value. Now, we graph the equation that's left, f of x equals x plus 1. So there's a y-intercept at 1, slope up 1 over 1. It's just when I get to where x is 1, I put a hole, up 1 over 1. So it's a straight line with a hole at 1. All right. So we say that the limit as x approaches 1, if I were to trace this, what's the position of the hole? What's the y value where the hole is at? It's 2. We can actually find that numerically by plugging this x value back in for x into the leftover piece. 1 plus 1 is 2. That's how you find the y value of every hole. Now, does f of 1 have a y value? Is there an actual y value? This is telling us what the limit is. That's what is the graph getting close to from each side. If this circle is not filled in, the f of 1, we say, does not exist. DNE is short for does not exist. All right, so notice what I did in the second one. I took the original function and made it a piecewise function. I said, let's use this graph for everything except 1. But at 1, I'm going to define my y value as 1. So we still keep this line with a hole in it. But when x is 1, y is 1. I'm going to graph the point 1, 1. All right, so the limit of g of x as x approaches 1. So as I approach the hole, that's where x is 1, from each side, what is the graph itself getting close to on each side? 2. But where is the filled in circle? Where is the actual y value at? That's right here. What's this y value? 1. So the limit is 2, but the actual y value is 1. All right, let's look at what happens with this one. This is just a straight line with no hole, no extra pieces, just x plus 1. So the limit as the graph approaches 1, getting close, getting close, getting close from each side, that y value that I'm getting close to on the edges of the graph is 2. Where is the actual solid? What's the coordinate point? 1, 2. This notation says what's the y value when x is 1. In this case, the limit equals the y value. That will become important later on, but these are just 3 different instances of limit notation. Okay, when we move on, let's think about if we have y equals some constant, say y equals 2. If I graph the line y equals 2, what is the y value all along the line y equals 2? It's 2, right? What this is saying is, if this is some constant number, I don't care what the x is approaching, the y value will always be the same number. So the limit as x approaches 1 of 2 is 2. If this is a number, the limit equals that number every single time. Because the limit tells us the y value, and if the y value is constant, the limit is constant. All right. Now, let's take this function, y equals x. What does the line look like for y equals x? It's just the line, oops, helps if I draw it correctly. Ugh, sloppy. It goes through the origin with a 1, 1 slope. 1, y equals mx plus b. Okay, so this point here is 0, 0. This point, 1, 1. This point, 2, 2. This says if this is x, what we do is whatever the number is approaching, I plug this in for x, and my limit is c. We call this substitution. I'm going to plug this number in for my x, and that's going to be my y value every single time. All right. These are the properties. If you want to take some time and write these out, I'm not going to wait for that. But these just give us basic properties. If I'm adding 2 functions, I just add the value of their limits. If I'm subtracting 2 functions, I subtract their limits. Mostly this is just common sense. All right. Example 3 is pretty straightforward. So this says as x approaches c, I'm going to plug in c in place of each x. I just substitute c in place of x. Same thing here. Plug c in place of each x. That's all this is. Mostly, we always begin limits with substituting. You take whatever x is approaching and just plug it in for each x. That's it. Now let's look at some actual values. The very first thing you will always try with limits is plugging in the number, just straight substitution. So as x approaches 3, if we can plug that number in with no trouble, that's going to be your answer. So we're going to plug 3 in for each x. And if you don't run into any problems, then yeah, I kind of skipped theorem 2 because I don't like theorem 2. Okay. But you're technically just looking for the y value, and we get that by plugging this number in for each x. Plug in 2 for each x. Whole bunch of 4s. So as long as you plug stuff in and you just get a number, that's your answer because that's your y value. All right, so I keep saying you don't run into problems. So obviously there's going to be a run into problems. Let's see what happens when we run into this. All right, so this is using the product rule. Do you notice if I just straight plug this in, I get tangent of 0 divided by 0, and if you have 0 in the denominator, this is undefined, I can't do a plug-in method. So I have to find some other method to make this work. All right, let's think about the general tangent identity. In general, tangent equals sine of x over cosine of x. So we're going to do a substitution. So instead of tangent of x, I'm going to write sine of x over cosine of x. And I'm just going to stick this x just in front of the cosine. I have to keep that x in the denominator. I'm just going to keep it in the denominator with cosine. Okay, now we're going to manipulate this a little bit. I'm going to put sine of x over x times 1 over cosine. I'm going to split this up a little bit. Do you remember this right here was what we investigated earlier with the calculator? What y value did this get close to? 1. So I can separate this out algebraically and find the limits of the pieces if I can't plug it in right away. All right, so I don't need to plug it in here because I know the limit of this is 1. But now I can plug in my 0 for this particular value because what is cosine of 0? 1. So I get 1 times 1 over 1, which is just 1. So there's many different ways we can manipulate things. You might be feeling like you have no idea what's going on. That's why it's helpful for you to watch this first. So when we talk about it again in class, it will make more sense. All right, this next example. I can't plug 2 in because I get 2 to the third minus 1 over 2 minus 2. If you get 0 in the bottom, you can't use the substitution method. You have to try something else. So if you see trig, typically your goal is to somehow get to this point where you know it's always 1. This is a polynomial function. What we're going to try with this is factoring. Now, I can't do any more with x minus 2. But x to the third minus 1 is a perfect cube. So what we're going to do is factor. Oh, you know what? This is asking us to graph. Okay, we can graph. Let me show you this first, though. I want to show you this way. Let's change this to 8 for just a minute. And I want to show you this first. If these were 2 perfect cubes, this can be factored into x minus 2. If you had me for algebra 2, I always say square the first to get the first, square the last to get the last, multiply them together to get the middle. If you can factor and cancel, you can plug 2 in to what's left over. So if this problem were x to the third minus 8 over x minus 2, you can use factoring to do this. Now I'm going to substitute my 2 in place of each x. So I get 2 squared plus 2 times 2 plus 4, which is 12. So that's if this were 8 here. That's the process you want to do. Example 6 actually says, let's graph this. I'm going to go back to the original problem now. If you go to your calculator and you put this whole thing into y1, make sure you use your fraction bar, that's green, alpha y equals n over d, that's your numerator over denominator. Put x to the third minus 1 in the top, x minus 2 in the bottom. And this has a asymptote at x equals 2 because that makes 0 in the bottom. So we have to kind of avoid that. Then it kind of looks like this and this. So notice if there's an asymptote, there's no y value that this graph is getting close to. This is going up to negative infinity. This graph is going to negative infinity. This one's positive. I think I set it backwards. So there is no limit when it's an asymptote. Now when it was a hole back here, holes, the limit exists because the graph is getting closer and closer to the hole. If it's an asymptote, there is no limit. So you must distinguish, is there a hole? Like here, if you cancel something from top to bottom, this is a hole. If there is a hole, the limit exists. If there's an asymptote, the limit does not exist. No limit. So we can look at limits from the left and limits from the right. So I would copy this part into the notes. And if you can't tell, this is a plus and this is a minus superscripted in the exponent position. Right has a plus sign, left has a minus sign. And let's investigate what that looks like. All right, the greatest integer function. You're going to have to really kind of squish this over on the side. So if I look at the greatest integer function, that's what int x is. That's the step function that goes like this. All right. If you want to know how to graph this on your calculator, go to y equals and clear out the function there. Then every time you're looking for something, push math, go over to number, and you're looking for int x. I think it's, well, it might not be number. Let me look. Yep. So push math, go over to number, and number 5 is int. Then you put in the x, and if you graph it, you just kind of see it all the way up. Okay. So let me show you how you read this. On this particular graph, I want to know what's the graph, what y value is x approaching from 3 from the right. So here's where x equals 3. So if I look all the way along where x is 3, where is it coming from on the right side of 3? If I go all the way up, where's the graph at on the right side of 3? See how it's right here? what is this y value? This is 1, this is 2, this is 3. From the right side of 3, the limit is 3. That's my y value. But where is it approaching? From the left side. If this is a minus, that means if I look along here, go to the left side, that's to the left of 3. What's this y value? 2. And this is kind of the sneaky piece, the sneaky part here. Okay? And probably the best way to truly get this is this last example, exploring right and left-handed limits. And what I'd really like to do is do this together in class. So if you get to this point, we'll finish this part up in class.